Hello and welcome to Creepy Puppets Presents. I apologize for being back to the terrible webcam today, but for my job I need to learn how to record a talk on Zoom. So that's what I'm doing. I've decided to share with you today a piece of research I did as a project for a graduate seminar in data science, specifically a graduate seminar using the R programming language to deal with biological, ecological, and geological data sets. So with that, I'm going to share the screen. There we go. Okay. So I want to talk to you today about digital paleontology using the NEOTOMA database. So for those unaware, I'm starting my Ph.D. in the fall, assuming everything goes well, at Lehigh University at the Earth and Environmental Science Department. And with permission of my primary investigator there and other people, I'm starting to work on my project now. It's a data science project using the R programming language, at least the first part is. And so I thought first I'd tell you a little bit about what my project is. So I've been hired on by paleontologist Dr. Bob Booth, who collects fossil and geological data and puts them into the NEOTOMA database. Most of what he does is using Peat Cores, which we're going to talk about in a second, to look at ecology in the last 10,000 years or so, looking at pollen counts, looking at testate amoeba fossils. And so I was brought on as someone who knew data science to help tame the data and improve the database. So an R package exists called NEOTOMA, and we're going to deal with that to handle the data. So the first part of the things I'm going to do for the lab is help develop a way to interact with the NEOTOMA package so that people can use the NEOTOMA database without having to learn R. So I should talk a little bit about what the NEOTOMA database is. It's a scientific database named for the scientific name of the genus of the pack rat. Pack rat hoards have been used by paleontologists and archaeologists to gain insight into the conditions around them for a long time. And so this database contains lots of data: pollen, insects, amoebas, crustaceans, diatoms, plant and animal fossils, and a bunch of inorganic data, as well as some archaeological data in the form of archaeological middens. The database link is there. So I should talk a little bit about what Peat Cores are and how we can use them. So peat is essentially a kind of biological sludge that is laid down by decaying plant matter year after year after year in lakes and bogs. Now, because things from those years get trapped in them, we can take a core, of which you can see on the right, of the peat, and then look at the different layers and see what the pollen was like, what the chemistry was like, what sort of critters are in there, and that'll give us some sense of the ecosystem when that layer of peat was laid down. Now, peat is rich in carbon because it's mostly plant matter. It can be burned directly, and it's what is eventually fossilized into coal. So it's a very, very important, not only for research, but also commercially. So in the R programming language, there is a package that already exists called NEOTOMA, lowercase, and I will use NEOTOMA to distinguish from the NEOTOMA database is how I will distinguish those. So this package can automatically download and process data sets from the NEOTOMA database in order to develop, to be used for further manipulation, for further research. And there are three kinds of objects in the programming language that represent three kinds of data. So we've got site data, which is name, location, some description. And then we have metadata, which is all the other sort of data about the data set. And then we have the data frame itself. So if I'm going to develop a graphic user interface to help people interact with the data that runs NEOTOMA for them, then I have to learn something about this NEOTOMA package. So I'm going to follow a set of examples given in Goring et al. These are the creators of the package, their paper. So we can start by downloading site data. So we can use get site command to download this information on Marion Lake, which is in British Columbia. And you can see it's got an ID, a name, a position, elevation, and a description. And then we can use the base $R call to bring that description fully out to us. So we can have this more detailed description of the lake. We can also combine multiple data sets into a single data set. You can use the base R command, rbind, to do that. So we can use the get download command to get metadata. And it's in, you can see these nested lists, not quite data frames. And when you have the output here, you get, see, we have the same information as site data. We also have our access, and we can see that there are three kinds of data here. There's pollen, there's chemistry, and then there's diatom surface data. So now we want to actually retrieve the data sets, and we can use this get dataset command to retrieve the actual data sets. Unfortunately, it's not compiled. The object Marion data is just a list of data sets downloaded. We can use this compile taxa command to bring stuff in, though. And I've done this for the metadata from the Louise pond, which is also in British Columbia. So we have these wonderful nested data frames that we can do stuff with. We can use this rather complicated call all the way down the nest, and we can graph. So for here, I've used ggplot to graph the depth of the peat core against the radiocarbon age, and as you can see, it's quite linear, and that's good. That's what we want. We would hope this is quite linear. But we can also convert it into more usable data tables using the base R data frame command. Here I have brought counts of the pollen Alnus against years before present into a single data frame so that I can graph them in ggplot, and you have this curve here. I should talk a little bit about the genus Alnus because it's the example I'm going to be using for the rest of this. So Alnus is the scientific name for the genus of the alder tree. It's closely related to birches. It's an example of a red alder leaf. So we might want to do some more data manipulation, having gotten this information into the site, into our computers, into R. So NEOTOMA automatically downloads analog as a package called analog as part of its machinery. So we can use a command, this tran command from the analog package to compute the percentage of Alnus over all types of pollen, which we can then put into a new data frame and graph against age to get this now curve of, my y-axis got cut off in this graph, of percent Alnus over year as we go back in time. So there's a couple of alternative methods of getting data besides the ones I've just described. So we can actually get data, site data, download data, dataset data by putting in a location vector, and this is essentially a square, and it will pull all the data from that square. So we use this get site with a location vector. You can see we've got 2007 records. We can also find the nearest site to a particular location. So this is the GPS coordinates of my house. Obviously, I've redacted them for public display. So we can use the get closest command to pull all of these things in, the my GPS as the vector. I'm looking for at least 5 records in any given location, and I want to look within 20 kilometers of my house. And I live in the Poconos, which is a very peat-rich area, so as it happens, there are a lot of records. In fact, there's 15,000 of them, including at Beltsville Lake, which is not far. It's actually in the valley behind us, not far as the crow flies, but because we live in the mountains, it takes about a half hour to get there. So going back to the percent Alnus over time, I wanted to do some more interesting data manipulation. I'm interested in sort of recreating population dynamics from pollen data. And if you look at this, you see it has a very nice exponential curve shape. So my plan is to use the least square, the nonlinear least squares method in base R to find a best fit exponential curve to this graph. If we remember that our basics of exponential curves, the formula is the principal times Euler's number, which is approximately 2.718, raised to the power of rate times time. So we need to find estimates of these values so that the system can work on it. So for the estimate of principal, I simply use the lowest value in the table. To find the estimate of rate of growth, I picked 2 points that looked kind of representative of the curve, no obvious outliers. I plugged the data in and just did the algebra, and we were able to get an R value. So we then put this into the nonlinear least squares command, and we spit back this lovely function that represents the best curve. We can now use the predict command to predict what the idealized percentage of pollen would be according to that curve, and then we can graph both the actual data and the expected data on the same graph using ggplot, which is that. And then you can see this is a very nice exponential curve. It's got some outliers close to present, and it's got some outliers way in the past, but most of it's fairly accurate. So one thing we can do is we can try to take that equation and turn it into an R command. And we can do this using a function definition. Now, I'm used to programming in Python, and Python's syntax for function definition is much, much better. This R syntax is frustratingly convoluted, but I did it. And so now, if I wanted to know what the expected population percentage was in any given specific year, even when we don't have data for, I can do that. So if I want to know what the projected pollen count would have been at exactly 8,600 years ago, I can enter it loo.funcs, which is the name I've stored this function under, 8,600, and I get a projection of 18.45% pollen of Alnus over the total pollen. So a little bit about the future of this research. I want to develop a graphic user interface to allow people to interact with NEOTOMA without having to learn to program in R. Graphic user interface is what everything is. Really, it's push buttons and mouse clicks to interact rather than entering things into a command line. Now, RStudio, whose graphic user interface I've been using throughout this project, the company has developed a wonderful package called Shiny, which allows for GUI creation as a web app. And I've actually used a program called Wallace in my current research. And I have high hopes for this project. And so basically what it is you program the commands using the NEOTOMA package, and then this just runs graphics on top of it. So here are the papers. Here's my images. I'd ask if you had questions at this point, but you can't speak back to me, so if you have a question, you can use the comments. Thanks. And I'm going to thank you very much for being my test audience. Take care.